So what we're trying to do is we've got an awful lot of blanks to go through, so what we need to do is figure out what changed ultimately across the across the top. So what things changed?
Carboxylic acid.
We've got a carboxylic acid and we have the chlorine. Okay. The carboxylic acid we didn't directly talk about, so this one's going to be difficult. You wouldn't expect to see this on the exam, but you should be able to do it from the textbook. The textbook does provide you the reagents to do it. Okay. But let's assume first that you know how to do this one, the chlorine. So how can we get the chlorine? What reagent gives us the chlorine? Do you guys know?
Really positive chlorine.
We need to generate a positive chlorine. How do we make that positive chlorine?
The chlorine with the aluminum, or something.
You could do chlorine gas, and we've got a couple options here you can use. I think you were saying aluminum trichloride is what you were aiming at. The other option that I would accept would be iron trichloride, so the equivalent to the bromine substitution. So we would then have to put that group somewhere on here. Okay.
Oh, okay, so it's just Cl2.
Yep.
I was like Cl2?
No, that's the C positive. How do we get that?
Yeah.
The next part's going to be a little bit trickier, so I'm just going to include the reagents. So we'll say you guys looked it up. Generating the carboxylic acid on the ring. I want to show this. So there's our abbreviation for the carboxylic acid. Comes from reacting a benzene ring that has a carbon with any number of hydrogens on it. So I'll just show one. As long as we have one hydrogen, this reaction works. If we have that and we react it with chromic acid, it's the one the book shows, that will convert or fully oxidize that carbon. Okay? So it's going to oxidize as far as we possibly can. I mean, fully oxidize. So it has nothing to do with how many hydrogens there are. It completely oxidizes it to its maximum extent, which ultimately means we'd be taking it to the acid. Okay? The other reagent, if you've got tutors, which you did.
You've talked about chromic acid, though.
Not in this circumstance, though.
Oh.
The other one that you could use would be permanganate, KMnO4. They both end up doing the same thing. They will fully oxidize that carbon, which gets a special name. What is that name for that carbon? Nobody? No, doesn't start with a C. Remember the common names of the functional for our aromatic structures? Toluene would work in this case, but the reactivity of that carbon gets a special name. It's a benzyl.
This?
That carbon is benzylic, okay, if we were going to describe it. So the chemistry of that carbon, because it's next to the aromatic ring, drastically changes, and that's why when we add chromic acid or permanganate, we can convert it into the acid. Okay? So that would be great if we started with a carbon with a hydrogen on the ring. We don't. So what else do we have to do? We have to somehow get that carbon onto the ring. How can we get that carbon onto the ring?
Make a positive carbon somehow.
We need a positive carbon. What reagent gets us a positive carbon? So we'll just be going back to our lists, also known as R's.
Oh, R.
The
Cl.
R.
So we could cheat and just keep it simple, CH3Cl with aluminum trichloride. The other one that you'll typically see that's a little bit more common, because this would generate a primary carbocation, or technically a zero-ary carbocation, incredibly unstable. You'll sometimes see it shown as the isopropyl chloride. This still works for this reaction, because we get the carbon on there, But what's that last bond? We do have that hydrogen, which allows the reaction to start. Once the reaction starts, it spits off anything else attached to it, including those carbons. So when we take this substituent up to that next one, we would be able to oxidize it down to the acid. Okay, and we'll show that with the isopropyl, because the isopropyl is a little more common. Okay, so now the question is, when do we do this reactions?
I would say you'd need to look at the final product and see what position they are at.
Okay, so we would need to evaluate that. We can simplify it a little bit further. Can we possibly do our second reagent first? Okay, the one we've got in here. Is this possible to do that one first? As our very first step.
No.
No, why not?
The carbon's in first.
We need the carbon there. So this would be our first step, second step, third step. Okay. So if we're looking at ordering, this one, how do I do this? Let's say A, B, C. C must come before B. Has to. We don't have a choice. Okay. Deciding where A shows up is the next issue, yeah?
Well, I was going to say, if that one were to go on first, it would be that carbon. If you were to then do the B step next, it would become fully oxidized, and that would be a deactivating carbon,
Exactly, right?
So then you wouldn't want to do that one first.
So
because
if we did C and then B, you're right. What would be on the group, or what would be on our ring, if we did C and followed it with B, is we would have that acid, which is deactivating, and it directs to what position?
the meta.
The meta position, which would put the chlorine here. If we look at our product, our final product has them substitute para. So the order is going to come in really important on when we decide to do these. Okay? So based on your logic, which step do you want to do first?
I'd want to do the A step first.
Okay? So if we go through and do A first, I'm just going to write A there. Yeah, I'm going to do A there. We would get our chlorobenzene. What step do you want to do next? We do step C, and we would get, oh crap, I'm trying to draw that again a little bit differently. There's our Cl. Where's our carbon going to go? Opposite as far as we can. We put it on the para position. Then what would we follow it up with?
The B.
Step B. Step B would oxidize, and we would lose both carbons out here, and they'd get replaced with oxygens. Where did those carbons go? Don't ask that question because I don't have an answer. Okay. They go off into the ether. They do something. Okay. So that is one possible answer. Is there a better one? What happens when we put the chlorine on? Is that ring deactivated or activated?
It's activated.
So our halogens were
Well,
tricky.
that's true. The
Chlorine
halogen was a
would need to
halogen.
donate electrons to be inactivated. Is chlorine willing to have two bonds? No. And in fact, chlorine would never be willing to donate electrons to carbon because
It's electronegative.
it's electronegative. Okay. So our halogens fall in this weird area where they are para-ortho directors because they have those lone pairs. But they are deactivators for the ring. Okay, so if we ran this reaction in this situation, as soon as we form our first product, we've now deactivated the ring. Trying to get the methyl on there, or a carbon on there, not going to be so easy. And if we're trying to get out of the lab as fast as possible, we don't like this method. Okay, so what we can do instead, we must keep C before B, but is there anything to prevent me from doing C before A?
You can do it last. Or, yeah.
We can swap the order of C and A.
Does it matter the order that we had it originally? Would you want a specific order?
Some credit would go to getting the correct order, yes. Not a lot, because it still works.
Okay.
Okay.
It just takes longer.
Yeah. If you put in where B came first, or B before A, then you would absolutely lose points because you definitely took it out of sequence. Okay. What happens if we do this? If we do C first, we get, whoops, it's an eraser. We get our isopropyl added. Okay. So that way, I'll redraw this so it looks a little bit cleaner. Our ring is now activated so that when we move to putting the chlorine on, it happens faster. Okay, which means we can get out of lab faster. And our product, there's our isopropyl and there's our chlorine, still goes para. And even further, we would expect it to be primarily para because our ortho is more sterically hindered because the isopropyl is so big. So we get an added benefit that we get a larger yield because we prevent the ortho substitution altogether, okay, which isn't as big a deal for you guys because I said don't worry about the ortho. Okay. Then we do B. Step B hydrolyzes, or not hydrolyzes, but removes the other carbons and gets us to the acid. Okay, so the best answer is to do put on the carbon first, then the chlorine, and then oxidize to our acid. Okay. Does that make, who was asking that question? You were asking that question. Does that work for you? Any other questions about it? Kind of zoom out so you can see it a little bit better. Makes perfect sense now. It's all written out, right?